Thank you, Dave, and welcome everybody. And this is probably the single one part that maybe some of you have been anticipating, so we'll just get started on it. So we're going to cover schematics. We're going to talk about a few different types of schematics. So we're going to introduce different types of schematics to you. Component identification, programming, troubleshooting aids will be identified. All of these are designed to work together to help you interpret and understand the circuit better. But let's look at a few different schematics. So I'm going to be bringing up some examples of schematics onto the screen. Forgive me, these are originally Randall McKinney style map schematics that I've condensed, so they're not going to look really good, but the first one we want to talk about is just a point-to-point schematic, which is one of the easiest schematics to read, at least when you're referring to where does the wire go, point A to point B. Sometimes some people refer me to talking about them, but at the same time, while they're the easiest to maybe read about, well, where does this one wire go from point A to point B, it also is the most difficult to interpret what the circuit is doing. So with that, I'm going to bring out what this handout is. I'll see if I can maximize it for better efficiency, but this is a standard engine manufacturer point-to-point schematics from an engine that's several years old nowadays. But we have a module, we have a terminal strip, we have a few light bulbs, a control switch, and we know that if we zoom in and are able to read the resolution on this, we can trace out and figure out where every wire goes. But there is absolutely no information here as far as what the circuit is doing, what one individual line on the circuit may do. It's nice to have if you're just trying to repair a wire or put a wire back in its place, but it doesn't get you there much when you're trying to troubleshoot. The second schematic, sorry, that was the first one. The second schematic I want to bring in is a point-to-point. Now, believe it or not, I'm sorry, it's more of a ladder logic type. This type schematic is, believe it or not, the exact same schematic that I just had up on the screen, but it's drawn out in what we call a ladder logic form. So not only if it's a little bit harder when you're trying to trace out point to point where do the wires go, but it gives some better understanding of the logic of the circuit and what's doing. And if you remember on the first schematic that I brought out, I circled right here in the center and said, oh, look, there's a module. Well, in this schematic, here's the same module, but now not only do we see connections on the outside of the module at different locations, but we can see some internal components and even some relay logic inside that module. So it's much better for troubleshooting purposes. My view has always been if we can understand the schematic and understand what is going on inside the schematic and know how it works, then we can troubleshoot it. If I'm blindly going into a schematic and I can't understand it, can't make heads or tails out of it, I don't know necessarily what voltages and what voltages should be applied to certain points of the schematic and when. So this is a worksheet, obviously, without you having a copy of a schematic in large life. We're going to skip over this part of the worksheet. And there's the second schematic that I had brought up a few moments ago on the ladder logic. But I just wanted you to see those two exact same schematic, but grossly different techniques about the way they're drawn out. So if we had followed along with the worksheet and some of the exercises, and the second ladder logic schematic showed the exact same information but added context inside the module, which I pointed out a few moments ago. This provided information to how the terminals on the outside of the modules are connected internally. The information still missing. This forces the person reading the schematic to have to apply some reasonable amount of assuming or testing to verify. And there's always that old statement about, well, I'm working on this unit, it's not working right. Well, there's a unit just down the road that's just like it. Yeah, I think every one of us in this industry has had to do that. Go down and find the one that's just like it, that's working, to see what it's doing and how things work. I don't think anybody should ever feel bad about that, because I know that I've done it on a regular basis, still do. But what we wanted to do real quick before we get into some troubleshooting exercises is kind of go through how we do a schematic at Ultronic. And some of this information is slightly outdated, so we'll just have to look past that. We've changed our title blocks and updated them with some new addresses and new icons. But page 1, if you look at any of our Ultronic panel schematics, page 1 is one of the most critical, and we're going to kind of just start in order and review each one. But if you focus your attention to the lower right corner, this is the area that displays the title block to the far right and the revision block. So the title block would be this part of the drawing, and the drawing number, to me, if I'm trying to help somebody over the phone to make sure I'm looking at the same thing they're looking at, this is always the most critical, as well as the revision block. And sometimes there's multiple revision numbers in this column. And believe it or not, I point this out because when I'm working with people over the phone, sometimes they have a hard time finding this information for me, because what I want to know is what drawing number they have, and I want to know what revision number they have. The revision number, if there had been, say, 2 or 3 revisions on this, it would be revision 1 on this next row, revision 2, and then revision 3. So the highest revision number is the revision of the drawing that you have in your possession. Now we're going to move over to the same page, but over to the other side. A lot of times, some customers will request, especially when we're mass producing certain panels, that we do an option block. And so they say, well, 90% of the time we're going to order the panel base, but there's going to be occasional times where we want to order the panel with an option, or later we want to order the parts kits to upgrade the panel to add a few extra options. This will also generally be on page 1, but there'll be an option block. Now, I have some panels out there that have 5 to 6 different options on them, but we'll generally give a description. In this case, this is a Caterpillar 3300B atom mounting kit for mounting that control system inside of a panel enclosure. And here are the part numbers that make up that kit. The top left of page 1 is generally reserved for notations, notes. So if it's a DD40 annunciator panel, it'll even have basic programming information in that area. There'll be numerous marks within the drawing that always reference C note 7, C note 5, etc., etc. Sometimes it's just general information. Sometimes it's something that's about parts that might ship loose with the panel. Sometimes it's about the fuse. I like this notation. Power to the fuse block must be disabled before inserting a fuse or lifting the fuse block knife switch. Of course, our fuse blocks are Class 1 Div 2 approved, but that's as they sit, not being serviced in working order. If we were to lift that gate or close that gate with power applied to it, there could be a spark during that time. So the notes are a great thing to be able to reference in these drawings. To the top right of page 1 generally is what we call the BOM, or bill of material. I found out to always call that out when you're flying air travel, commercial air travel. Don't say BOM, say bill of materials. Every item through the drawing of the schematic will always have an item number referenced on it. That item number can be looked up into this table. You can get the manufacturer's part number for that item number and a short description of it. So if you're ordering, let's see if I can give you a good example of something that might be a common part to order. Well, here's a terminal block, a multi-level terminal block assembly. There's a good part number for it. If you're trying to call up or email Electronic Controls Panel Division to get replacement parts, pilot lights, escutcheons aren't, well, yeah, they're going to have a little bit of a part number, but they're going to reference the drawing number and the serial number. I was actually looking for a relay in here, but I don't see it right off the top of my head. I'm sure it's hiding in here somewhere. If you have one of these this is all based on a flex panel, by the way, designed around modern day Caterpillar engines. If you have one of those, there'll be a 50 k ohm pot on the front of it, 10-turn potentiometer, and there's our part number for it. So it's real easy to look up part numbers if you have the set of schematics and you know what the item number is. You can come here to this table to look it up for ordering replacement parts. So in general, now we're going to move to page 2. In general, page 2 display details about the panel enclosure on most drawings, not all drawings. I'm just kind of following a general layout that we try to kind of follow. We show all types of details on these. This first one is that option that I was showing you that was listed on page 1. Here is an actual drawing for that option. So all this is an insert kit, a little enclosure that can be installed into the main enclosure to house a Caterpillar control system that comes with a particular engine. I think this one is actually for the 3300 Atom 4 engines. So make sure I didn't skip a page. Okay, so also on page 2 is generally a enclosure layout showing multiple things about the dimensions of the enclosure, what type of doors on it, where key things are that are viewable from the outside of the enclosure. Sometimes you will see some back pan layouts on the enclosure or on the system, how things and details of how the internal components lay out inside there. So in some of the drawings, the second page will be available. This would be identified as page 2A or another page 2. That will show, again, more DIN-rail detail. If other pages are necessary, the numbers will be consecutive, 2B, 2C, etc., etc. This only occurs when the designer wanted to include additional details that are related to the enclosure view or higher resolution views of the DIN-rail detail, how things are laid out on the DIN rails. You're not going to see this on every panel. Again, this mainly refers to if the panel is a mass-produced design. We're going to skip over the exercise, but I will zoom in on figure 5.6 at the bottom for a moment and just point out that we can tell by looking at it that is a 3-level terminal block. What the designer did on this one is they showed what is at each level of the terminal block. The lower level is shield blocks down at this end, 5-volt supply down at this end, shield in the middle at this top end, as well as A-common wires. They're commonly called ACOM, but they all revert back on a DE3000 system back to a particular terminal on the primary terminal board with a ground symbol. So it is a ground. It is connected to battery voltage ground ultimately, but because it is through the DE3000, we'll always single it out and call it something slightly different. So it's ACOM. So it is a ground. And then finally, the upper level, still a shield block at this end, but these numbers are 801 through 806. So if anybody's very familiar already with 0 to 5 volt pressure transducers commonly found in the Ultronic panels, you can kind of guess that this is a terminal block assembly for pressure transducers. And again, we're going to skip over the exercises because you don't have these schematics available to you in front of you. So one of the other things that you might see is a board like this, or some board details. Now, these could be any product that's found in the panel. This one happens to be what we called a flex panel PCB. It was developed in 2017 for the flex panel series. This was any 5800-333 drawing. There were several different variations and customizations and options for several different customers. This board, if you've never seen one, it looks just like a relay board. It technically is, but think about it also as a wiring schematic mounted on a board. Two reasons this was developed. Speed of assembly, speed of delivery to the customer, as well as improved reliability, because it reduced a lot of human wire connections that we would normally find in a panel. It also cut wiring time on the panels down in half. But this gives just a visual representation of actually physically what the board would look like, and it gives some wiring indication of where you will see wires connected going elsewhere in the panel. Now, don't worry, those same wires and those same connections are shown elsewhere later in the design. Again, we're going to skip the exercise and move straight to page 3. Page 3, by the way, generally in most designs for a DE product, page 3 has become where we see, at least in a 3000, I apologize, 4000 might be shifting a little bit, but page 3 generally displays the actual DE3000 terminal boards. And we do a lot of detailed information on those drawings that sometimes get overlooked. So we will follow this exercise for a minute. Locate the stop, run, start switch, which is right here. Item 9, what position is the stop, start switch contact drawn in? So now we know it's drawn and opened. That's the easy word that everybody likes to write there. But if we look at the wording, stop, run, start, and we notice that there's a dotted line here with an arrow coming back, that's a great little symbol indicating that that's a spring-loaded position, so it's a momentary position. It'll spring back from start to the run position. We also notice that both the run position and start are dotted lines, while the stop position is a solid line. So the correct answer here is not open, but in the stop position. If we want to say stop and opened, we can do that too. What position must the switch be in to close the contact displayed? Now this is a fun one too. So in general, when you see these switch icons in an Ultronic drawing, you're also going to look real close. You're going to see a OOX. So we know that with this arrow right here and this wording that there's more to this switch or another contact block somewhere else. In this case, it says page 7A through 7E. But the question is asking this contact that we're looking at. So what position must the switch be in to close the contact displayed? And the answer is the third position, or start position, because we can see that O is the first position, it's opened. O is also the second position. X is the third position, momentary. So now, if we know how to interpret that icon in this schematic, we know that when this switch is momentarily held into the start position, because it's a spring loaded with that spring symbol, it's going to close this contact and it's going to momentarily ground the R terminal back into A common. And we know that A common is a ground, and there's the terminal right there that it ties to on a DE3000 board. So again, if we know how to read a schematic and interpret the things that are in the schematic, It helps us troubleshoot and know exactly what's going on. If I were to measure between 24 volts and this terminal, I should have 24 volts because I have a good ground. If I did the same on this side with the switch in the stop position, I would have nothing. But when I closed the switch and did the same measurement, all of a sudden I should see 24 volts because now I have a good ground here. So using voltage, a known voltage source with your meter and coming with your negative probe for your meter to take measurements that complete a voltage path or voltage circuit is a great way to troubleshoot circuits out rather than using what a lot of people want to jump to as an ohm meter. Any questions about this page? Because I kind of got detailed before we moved on. I'd love to have somebody ask a question. Okay, that means I'm doing my job right. So we've covered pretty much that exercise and explained that. Page 4, other accessories. So let's take a look at what maybe page 4 is. Okay, so page 4 of the schematic that we're using, again, it's a flex panel that we're kind of following. It's just the Ultronic telematics or telemetry module, the TE1000 that we manufacture. But again, it's useful information, shows how it's getting power, and it shows how we've dictated some of the communication things are going to hook up and where they're going to hook to. It also tells us, hey, go look at page 3 in the drawing for additional connections. Page 5 displays the pressure transducers. I'm praying right now that the next page that comes up in this exercise shows an actual example of page 5 because we do have an exercise here. So let's just advance and see what happens. No, it doesn't. Okay, I apologize. So let me do this. I'll actually bring up page 5 from this drawing right now. So this is actually a really good drawing to look at and understand. But what we show is now I showed you a version earlier where it was a physical bird's eye view looking down at the top of a 3-level terminal block. Now, to add to confusion, when we get to this page, we draw it out just a little bit different, but understand that the side view of the terminal block is just like this. So the lower level ties from one side to the other, the middle level ties from one side to the other, and the top does the same. And we show this on the drawing to help you understand this, but we also say that we reserve the bottom for positive signal, middle for a negative or a ground signal, and the top for the actual variable voltage signal. So here we show our standard Ultronic pressure transducers. We do color the wires red, black, white, coming into those 3 different levels. We show how we have a 5-volt supply coming in, and it's kind of hard to see. It's going to be hard for me the way I'm showing it and sharing my screen for me to zoom in and out. But we do show a small little tiny connection of this 5-volt wire as it comes across being jumpered into every terminal block. The same thing with our A common and black wire, goes across and does the same thing. And then the signal wire, the white wire, comes all the way up to the very top level, and it translates right over into the wire that goes up to the channel on the DE3000. And by no accident, these wires going 801 through 806 guarantee you they all land at channel 1 through 6. We do some pneumatic detail in the schematic. Again, this is an electrical class, so we're not going to spend a whole lot of time on that, but does anybody have any questions about this before I advance back to the presentation? Okay. And I'll see if I can get this back to full screen. Okay. So page 6 generally becomes the main section of the schematic where we start showing a lot of things in details, where the power comes into the panel, how the power is distributed, the meat and potatoes, if you will. If there's any relay logic going on, that is the main, what I refer to as the troubleshooting pages. Now, I'm going to bring that other schematic back up shortly, but before I do that, I'm going to continue to run through the presentation just to talk about a few of the symbols. So we'll jump straight to the bottom of this page, and we'll just cover a few common symbols commonly found on an electronic panel. So the first one, fuse, FH1. It provides the label identifier on the PCB. So again, remember, I said that this panel that we're looking at has what we call a flex panel PCB. And you'll probably, hopefully, be seeing more of that as time goes on. More of those systems are in development. We have another one coming up one day soon for a DE4000 panel design. And what that does is it allows us to put more items in a panel in a more of a compact manner, but there's nothing super secret about it. We show the schematic of the board embedded into our drawing. So when you see these boards, if you ever do, just think of them as a wiring harness for the schematic mounted on a board rather than a handful of wires. It eliminates so many wire connections, and we've definitely seen positive results that it helps us bring panels to the customers quicker, but it also makes them more reliable because it eliminates so many human wire connections. So that means we don't put wires in the wrong place. That means that wires can't come loose because they're on a board. But this is a classic fuse, 3 amp. We'll advance to the next page. Power terminals. So a lot of times when we have products in the panel that we're just trying to get power to them, we'll draw them as rectangle blocks. We'll show the negative side, generally with a 102 coming into them. 102 in an electronic panel is always battery ground. We'll show whatever power is powering up the positive side of the device. This device could be a DE3000 power supply system, but it could also be other accessories or even DSG gauges or air-fuel ratio systems that are added to the panel. They may look very similar, but they'll always have, generally if they're drawn out and using this symbol, they'll have our part number in this area. They'll have a description as to what it is, as well as an item number that reference the bill of material back on page 1. Switch, 2-position switch. Notice 1, 2. Notice the solid line. Notice the dotted line. So the switch is drawn in the manual position as described for what it's described as doing. Light. The description tells us that it represents what it represents. In this one, a compressor oil pressure permissive, or a compressor oil permissive, sorry. It is a pressure because it's green. I just happen to know that. The letter in the center indicates the light color. See, I said that too quick. A relay coil. The description identifies that this is for indicating the DE3000 status. That is incorrect because that says auto speed, doesn't it? So I've got a little problem there. The relay is numbered, in this case CR1. This is indicated by, okay, I definitely used the wrong icon to create this. Every relay in the panel will be numbered. This helps when locating the contacts for the same relay elsewhere in the schematic. The coil terminals are also illustrated. These contacts are polarity sensitive. A1 is always positive, A2 is always negative. A relay coil can be turned on and off by adding or removing either the positive or negative supply. Okay, so about the second half of this paragraph is true. The first half is slightly false because I used the wrong icon here, but I will say this. The description of what it does, the relay number, A2, A1, so we automatically know A1 has to have positive power on that side to turn it on and off. A2 has to have negative power. The item number, in this case, item 27C. So if we were to look that item number up in the bill of materials, we could order a replacement component for it. Oh, one other thing. In some of the newer drawings coming out, what you may see is you may start seeing page numbers associated with this. Those page numbers would show you what page to go elsewhere in the drawing to find the contacts. So now we're going to do the contacts. So a normally open relay contact, this symbol illustrates the relay with its function description and relay numbers. So in this case, it's a start gas valve relay. It's linked, it's an items 27C as well. It's a CR7. It tells us page 6. So I can guarantee you what this means is if I go to page 6, I will find the coil that energizes to energize and close these contacts between 11 and 14. Normally closed relay, much the same, except we have a line across it, same thing. It gives us description, an item number, a relay number, the page where we can find the coil. Now, I think last week we did the relays and semiconductor section. So you can see in both cases, 11, remember, is common. If it ends in 4, it's normally open. Now we're using the second set of contacts in this next relay, but it ends in 1, so that's the common. And if it ends in 2, that's a normally closed contact. So just wanted to kind of throw that in from last week. So notice the difference between these two symbols. Relay contact should always be illustrated in a non-energized self state. That is the general rule that we follow. I'm not going to say we get that perfect every time. So now, you're not going to see this in a lot of drawings unless they do have these PCB boards that I've been telling you about, but we're going to talk about them anyway. Chevron. This indicates a junction in the circuit has occurred. It's used to indicate that the path of the circuit has transitioned from the PCB, so that little relay PCB board or flex panel PCB board that I've been calling it, to one of the two harnesses or vice versa in most cases. So you'll see this icon in the drawing, and you notice that, hey, well, it's still wire 103, true. But in this case, it was on the PCB, actual part of the printed circuit, but now it's transitioned through the connector onto a wiring harness. Now, on that particular board, there's two wiring harnesses, so we number them wiring harness 1 and wiring harness 2. Fuel gas shutdown valve, diode blocks, what we really want to focus on. So last week we talked about diodes, and we talked about how they're used for reducing self-inductance, or the slang term commonly used in most cases is just a flyback diode. So they're used to provide an area for, also used to provide an area for the user to connect accessories to the panel. In this case, we have a 24-volt solenoid that this customer has out on the compressor package skid floor that, once energized, will switch on a pneumatic source to allow an automatic valve to open. When de-energized, the valve will return to shelf state and close. So here's our diode block. Here is our symbol to represent the customer's magnetic coil that they're going to wire to it. We have a 102 feeding one side of it and a positive voltage source. In this case, it happens to be circuit 115 feeding the other side. Notice also that both wires do not carry a color. In this case, they carry a wording of a PCB, meaning this is found on that relay PCB board. Now, why is this interesting? One, we drew it out for our customers for troubleshooting purposes, just like it would be if it was a gray diode terminal block snapped on a DIN rail as an individual part. So it's easy to follow, easy to troubleshoot. But what's really interesting again about this is because it's part of the PCB, there was no physical part that a worker had to put in and wire in. The wires are already run, the wires are already connected to it. It's part of an integrated circuit. Any questions on this? Great, we'll just keep advancing. The next one's emergency stop. I have a lot of fun with these. Two type symbols can be used. The symbol will always include notes to identify it. Note the position of the switch contacts, meaning the contacts are drawn below the actual wire contacts. When the switch button is pushed, we'll push the top of that button, the contacts will open. This is a fail-safe design. So everybody see that? So the wires come into each side of it. They need to be connected, but when the operator pushes that switch down, some people call that a mushroom head or something like that, these contacts will go up. Now, I have seen mistakes in drawings before where this contact is actually drawn on top, but this is the proper way. Output, and sometimes too, there'll be a little arrow under this that might reference other pages, other locations, because the same ESD button could have multiple contact blocks on it, so just be aware of that. Output module. So think about a DE3000 for a moment and think about the power supply board. We have 4 output modules on it. They're always located on the power supply. They are polarity sensitive solid state relays, but we don't ever call them relays. We refer to them as output modules because we don't want to get them confused with the other devices elsewhere in the panel that are mechanical relays. Okay, so when we draw this out, it's pretty simple. We'll always put a note in here that says DE power supply. We give you the item number. It's an output 3. And we give you the item number for the actual output module that mounts on the power supply board. We show what wire's coming in to the positive side of it and what wire's going on to the negative side. We know that positive voltage is over here, more likely feeding through, feeding a load over here. That's not always true in every case, but they are polarity sensitive. So if I'm turning on and off a ground signal, I might bring in a ground signal here with a load or what needs to see that ground signal coming out on this side. We also generally always put notations in here. We'll say closed at, in this case it's closed at auto start, open on fault, 0-second open delay. We do have an extra notation in here that says 60-second off delay option for post loop. So not only do we have the way it's defaulted, but we also give an option way that the operator could go in and reprogram it. Now the only thing that's missing from this is there's a really faint dotted line that looks like a normally open contact for a relay drawn in here. And for whatever reason, when we made this, it didn't transfer real well on this one. Now you can see the same thing kind of down on the next section, but this is a digital output. At glance, it looks exactly like this output module here. There's 8 of them on a DE3000 terminal board, but it's slightly different. Notice the 3 plus and the 3 negative here. This one just has a 3, nothing here. We can see the internal contact here, which is good. And in our schematic, how we would place in the schematic, this dotted line, internal dotted line would go on and connect to at 102 in the panel, which is what? Battery ground, always. And I haven't seen an electronic panel, well, in the last 10 or 12 years that 102 wasn't battery ground. Again, we give notes. It's a DE3000 terminal module. We give the item number. We tell you it's digital output number 3. Now here's a fun part. Everybody misses this one, especially the new guys that are coming to our industry. We tell you what channel it's linked to. In this case, we say channel SO1, which is speed on the DE3000, high control set point. And in this case, it says closed when engine above crank RPM. So for whatever reason, out of context, because we're just looking at this one symbol, we need to identify when we get what we consider above crank RPM, and we need to close this contact to do something. But in reading the schematic and in reading the notes in the schematic, digital output 3 which that's what this is linked to channel SO1 high control set point. So now we know exactly where to go and what to edit if it's not happening inside the program or through the keypad of the DE3000. Panel terminal blocks. Square block with a number in it indicates a simple terminal block located inside the electronic panel. Not shown, terminal block on that PCB. If we have a terminal block in the drawing, and you'll see it when I bring up the main drawing, it's going to also be a square, but it's going to have a very faint dotted line, ghost line dotted around it, very similar to what you see here on this icon. So just be aware of that. It's also always indicated by item number. Engine terminal block. So if we're interfacing with a Waukesha engine or a Caterpillar engine, a Cummins engine, and we're going into their engine control panel, we generally will rotate the square icon to make a diamond. It'll always be a dotted line indicating that it's not ours. Furthermore, if we have wires in one of our panels that indicate it's not a wire by Altronic, but it's a wire by the customer, those lines will always be indicated by a dotted line in place of a solid line for the wire. So page 7, we're going to move into the main engine interface pages. We'll see if we can touch a little bit on those before we get into the bigger part of this. Some engines nowadays, as you know, come with computer systems on them. And there's definitely options on those computer systems. There's definitely different ways to program them. Well, I'm where I came from, where I worked at my last job, I used to always program them like this. That's true. You can. More so lately, most of them have been getting a little bit better about not giving customers too many terrible options, like they kind of have a default. There are some out there in existence, though, that give you way too many options. So anybody can program that engine any way they want to. And those are dangerous because when we're trying to get one system, an Altronic panel, to interface with another system, engine that can be programmed any way under the sun, but generally doesn't mix real well. So what we do is we follow whenever an engine manufacturer comes out with a new engine design, new engine interface, we get what they call a customer interface guideline. So yes, we have a group of schematics so we can test and understand exactly how their system works. And we sometimes find flaws in their systems, and we sometimes deviate how we interface with it because of those flaws. But generally what we try to do is we follow their engine customer interface guideline. And if they're talking about input 3, such in this case, can be programmed any way, but we're going to say, hey, we're going to use input 3, and you must program it this way. What they don't do real good in their notations is necessarily tell you what terminal number input 3 does. But when we do our engine interface sections, we have that singled out to the correct terminal. So as long as you wire it up the way we tell you how to do it, and as long as you program your engine how we recommend you do it, the engine should start, stop, and control properly. So now we're moving through the schematic a little further. Page 8 provides information on some wiring options, main sequence of operation, relay details, etc., etc. One key thing, I think it was 2014, we introduced the DE3000 enhanced system. Yeah, the second half of 2014. And prior to that, people used a DNFT only or some kind of loop no-flow device, which was just a standard on-off switch. It was either normally open, normally closed, etc., etc. But we introduced the option of being able to use a proximity switch. So on a 3000, those happen to be channel 27 and 28 that have the capabilities to do the loop proximity switch. So that's generally where most designs moving forward after that time period, we slated for loop no-flow devices. But we make sure to try to still show the customer that there's 3 ways you can wire it up. If you simply have a DNFT or some type of a switch, You can wire it normally closed, where if the switch faults, it'll go open, shut you down, a little different programming option. Or you can jump to the two terminals for the channel together, wire the switch normally open to ground. When the switch faults, unit goes down. Or you can wire it using the proximity switch. Now, this drawing stemmed from a very early drawing with a proximity switch, and it doesn't necessarily have to be done this way. What they're doing in this one is they're jumping the two 27s together, going one wire out through the proximity switch, returning, and going into ACOM, or battery ground. Most of my guys that I deal with on a regular basis don't even look at this. They wire, most proximity switches have a pair of yellow wires. They wire the two yellow wires straight to channel 27 with no jumper. Works just fine and dandy. In fact, it's an easier way. So we have talked about maybe updating this icon to simplify things for a lot of our customers moving forward. Any questions about this one? Because this one does seem to rub people sometimes. Okay, good deal. All right, so towards the last page of the drawing, sometimes we'll start showing some customer contact options. And some of those contacts include options to operate a chem hot start. I think they actually dropped the K these days. Last time I talked to any of these guys, they just go around wearing shirts to say hot start now. There's two examples. The standard is compressor hot start 24 volts amps, engine hot start 24 volts DC. I'll just tell you what we're doing here on this one. This relay would be energized when running because it's based on whether or not the Caterpillar engine is running. So this would be 24 volts to stop the chem hot start. It does say that notation up here. Engine compressor chem hot start energized, chem hot start on when engine off. Some people like to reverse the way, it's rare, but some people do like to reverse the way the chem hot start does. Hot starts do have notations in all their drawings that say how to do that. It involves moving one wire. This one, engine compressor chem hot start energized to chem hot start on when engine off. So what they've done is they've just moved the contacts to where it's receiving 24 volts when the engine is down through a normally closed contact of the relay. Now, one reason why I like to use this relay and point this out is it's cat run relay, it's CR4, both relays. Terminal 22, terminal 24 go to different places. Terminal 21, shown twice, go to one place. There are not two terminal 21s on that relay. Terminal 21 is drawn twice to indicate two different states of that relay. There are still only three terminals on that relay, 24, 22, and 21. We just draw it twice because we draw it in two different states. So please make note of that. Any questions on that part? Okay. So I'm going to switch back, do my best to switch back to that other drawing, and now we're just going to kind of have some fun. But there's a couple of things that I do like to point out. I'll tell you what, I'm not going to go full screen so I can zoom in and out as we go through this. But if I'm troubleshooting something, and I'm just going to pull up some examples. If anybody has any questions, scenarios, this is the time for this next hour where say, hey, I was working on X, I had this problem, I troubleshot it this way, we'll do our best. If you have a drawing number, I could even, if we have time, I could possibly even pull up that exact drawing number and we can look at it. So this is for you guys. But one of the things that I like to tell people that I do when I'm troubleshooting something is I generally kind of start at the beginning to kind of understand what's going on, but I also jump to the end real quick. And in this case, what we're going to do is we're going to pick on a 3500 Caterpillar Atom 3 system. And we'll use just a quick example. Maybe a gentleman calls me up and he says, well, hey, my unit won't start. Okay, I get that one a lot. What's it doing? Well, it just doesn't start. No, it's doing something. So I'll go here and look at the engine interface page, and I'll zoom in so we can see. And maybe maybe I start prying him a little bit for information, but maybe I don't. But what I do is I look at the schematic and I know two things. I have a digital return coming in from the Caterpillar engine. It goes through our circuitry. Notice it lands at DR. Item 27, if I look it up in the BOM, is that relay PCB board. It goes from a black wire, transitions through this terminal. Now it's still this circuit, but the circuit's on the PCB, so it's part of the printed circuit. It leaves through a wiring connector, the harness, in this case, wiring harness 2, and it wires directly to output module 1 and output module 2 on the negative side. So right there, I know without knowing much about this system, because remember, these are polarity sensitive, because they're solid state output modules / relays. Don't ever call them relays though. That this is a ground. That's a ground coming into this side, and this side is a load. So now I know that if I follow this out, now we call it wire DER, it's black, but it just entered in to the PCB board, or the PCB, sorry, and at terminal DER, the customer must wire it to CAT terminal 17, and it says what we're supposed to do. Driven equipment input, electronic controls panel will ground to enable run. Unground to shut down, no cool down. Okay, cool. So we probably need that for it to start. A second thing that we notice is that output 2 closes for the CAT start signal. It goes through a switch. Now we looked at a switch earlier. It's drawn in the stop position. It's 0XX. So we know that when it's in the run position or the start position, this contact is closed. We travel onto the PCB through a wiring harness connection. That is a misprint. That should actually be wiring harness 2, by the way. And then we enter into a relay, loop permissive fail relay, go through our start signal, and we return to CAT terminal 16. All in all, everything that I just pointed out is a pretty simple circuit. I don't think we'd have that many people disagree with that, but it could be a booger bear to troubleshoot. So what I'm going to do real quick is I'm going to point out some things that I've learned to walk people through how to troubleshoot this circuit, because I'll get the phone call, my unit won't start. They love to blame the electronic panel. 90% of the time when I get this call, there's nothing wrong with the electronic panel, but this is going to be a quick way to prove that out. So if I know that this is a ground, remember one of the things that I said I can do. It's kind of hard to take an ohm meter and ohm between what we think is a ground and another ground source and verify that we've got a good ground. But what's real easy to do is to use a digital volt ohm meter and you put it in voltage and use it as a voltmeter. So I can pick up a 103 anywhere in the panel, which is positive 24 volts coming into the panel. And I can do a test first. I can measure voltage between that 103 and any 102 in the panel, which we know is a ground. And I can verify, oh yeah, we got 24 volts. Well, if 15 is a good ground, then I should be able to go to that CAT terminal and put the black probe of my meter there while I'm leaving the red probe of my meter still back on a 103, and I'll get 24 volts if this is a good ground. Well, I know now that CAT's generating a good ground. So now maybe I want to trace back. That's supposed to pass through my whole board, my whole system, and return back to these two terminals, one negative and one positive, on the power supply board at terminal 1 negative and terminal 2 negative. So I can do the same test. If I touch the black probe on my meter here, and get 24 volts, then I know that this is actually a good ground. Is anybody not following this? We got time. Okay. So the next thing I'm going to do is if I'm in the stop mode, I'm going to do two more checks real quick. I know that this terminal 17 comes straight into a DER terminal at my PCB, travels through my PCB, and then out of a wiring harness connector, and it also wires to one positive. I have no voltage here on this side. It's just I have a good ground is what I have. But with a CAT system, if I measure voltage between ground or 24 volt positive, I should actually see something here. And this is a way for me to check this terminal. This terminal is coming from Caterpillar, and it's looking for ground, but it does something. Now, I think earlier this year we did a DE3000 class. I'm not sure if we did a digital enunciator class, but we talked about digital channels on a DE3000, or discrete channels, or sometimes referred to as normally open, normally closed channel on 3000. In those cases, what we said was, we said one terminal, let's pick on channel 10. We said one terminal was producing 5 volts. The other terminal for channel 10 was looking for 5 volts. Now we could wire them in a normally in a closed loop situation or a closed loop switch in device. So we'd send the 5 volts out through the end device, maybe a vibration switch, and return back. Or we could jumper the two channels together and send one wire out to an open switch. But when the switch closed to ground, it would sync that 5 volts to 0 because it was a non-incentive voltage. Now, for those of you that have been through some of this electrical class, I think we showed it last week too, that's also a reference of what we call voltage potential, almost, just like it, which is why I like to use that video so much. I don't think we need to show that video today. If any of you missed it and want to see it, you can go to the YouTube channel and watch it. But here's what's fun. When Caterpillar has a digital terminal that's looking for ground to do anything, they do the same exact thing. They give a reference voltage there. It's a non-incentive low voltage. It's a voltage potential. It's designed to where CAT's monitoring it and saying, yeah, I got voltage there. Yeah, I hadn't been grounded. But as soon as we ground it, that voltage sinks to 0. So what I might want to do as a really quick test is I want to come right here and measure between ground and this terminal to see if I'm getting any voltage from CAT. If I'm not, I might now want to jump straight up to CAT and see if I have any voltage. Now, the fun fact is that you won't get out of a CAT book anywhere. You'll just get it from people like me that have done this a few times. CAT's digital reference voltage is 12 volts. What really will throw you off on that, being that it's a 24-volt system, is if you measure voltage between this terminal 17 or this point here even and ground, you're going to see 12 volts. If you do the same thing, measure between this point and 24-volt positive, you're going to see 12 volts. Now, the polarity might change, but the reason being is because we have a 24-volt system, but CAT's sending me a reference 12 volts. So it's half of 24. So whether you're measuring voltage from ground or whether you're measuring voltage from a positive source back to the 17, you're going to see 12 volts. Now, it may drift just a little bit, but 11 to 12 volts is about right. So if I pass that test right there, the first thing I know is, hey, I'm sending or I'm receiving a signal from this. So I've got a good electrical connection all the way up to the source in the engine where this comes from. The next thing I might do is stop right there, or I might come down and check voltage on this terminal 16, because this is the start. We have to ground this to start. So that means there's reference voltage on it as well. Now, we can check it at CAT 16, or we can come right up here to this ST terminal that's mounted on the edge of that flex panel PCB. It goes through this relay, but this relay won't close unless we have a loop permissive. So we need to go and kind of troubleshoot that a little bit. So for right now, what we'll do is we'll stop and we'll say, okay, well, Mr. Mechanic, try to start the unit. And we'll ask him to go and watch the red LEDs by these two output modules. And what he should see based on the program is we should see that this one for driven equipment turns on first. Close when GE ready. Open on fault, 0 second open delay. So at startup, close when ready. At startup, if we go into a ready mode, we should see the red LED for this one to close immediately. At that time, if we are monitoring and measuring voltage here coming in from CAT, we should see it sink to 0 because it's just been grounded by 15, we hope. Okay, the second thing we're going to say, hey, did output module 2 light up? And he may say, yeah, it did. This happens to say close for CAT start run, open on fault, 1 second open delay. It doesn't really tell us when it closes. We happen to know that if we're pre-lubing a 3500 though, but we're going to generally wait about 60 seconds for it to pre-lube. So he says, yeah, both lights turned on. Okay, well, we want to test and make sure that this output module is working good. So maybe what we do is we repeat our original test where we're measuring from a 24 volt source to this terminal 151 or this wire 151 at the back of this stop, run, start switch, to where as soon as this output module turns on, we should see what? A ground here. So if we're measuring from 24 volts to this point, all of a sudden, boom, we should have 24 volts registered on our meter. If the light remains on and the switch is in the run position, but we want to test the contacts of the switch, we can jump right over here to this side and do the exact same thing real quick. We should still see 24 volt reading. Again, we don't have 24 volts here. We have a ground all of a sudden here. Make sense? So the last thing is our loop permissive fail relay. So maybe in what our case is that we get all the way through all the troubleshooting, everything's passing, everything's working up to this point. But we come over here and we say, well, I still seeing 12 volts. If I go from 24 volts to this point, this ST, or 16, I'm still seeing 12 volts. Well, that's because, again, we're getting that 12 volt reference voltage back here. So that means the only thing that it can be is we got a problem between this point and this point. So CR3, page 6. We're going to go look at page 6. If I can find it. Ah, there it is. So CR3 is right here in the middle. I'll zoom in. We know that CR3 is our loop permissive fail relay. We know that it receives 24 volts all the time. We know that it's grounded by digital output 4. We know that channel 6 high control set point, it says close when compressor oil pressure above permissive. So now we know that the rest of the circuit, all of a sudden, well, wait a minute. This relay has to be energized. Oh, wait, it's wired to an LED on the front of the panel. This LED has to be on too. Will be on if this relay is energized, but this relay has to be energized to do what? And if I jump ahead, back to our original drawing, to close those contacts and allow the ground that's maybe hanging out over here to get through to terminal 6 on the Caterpillar engine. Sorry, I'm jumping around all over the place. So the next thing I'm going to ask the tech over the phone is, well, you know, when you were starting this thing, did you happen to notice that green light on the front of the panel light up ever? No, it never lit up, he says.
And I said, okay, well, sometimes those lights burn out. Can you verify while it's cranking, did this relay ever energize? He says, well, no, it never energized. There was a yellow LED on the front of it. There's a light emitting diode. We can see that symbol right there. So we know that when this relay's on, it's going to light up with a yellow light. He says, no, it never did turn on either. Well, so I tell you what, did your compressor prelude? He says, oh yeah, it prelude for quite a while. Did your compressor build up oil pressure? Oh yeah, it built up oil pressure. Okay, well, go into the menu system and go into the control set points on the menu system and look at channel 6 and tell me what the high control set point set to. And he says, well, somebody set that thing up around 99 pounds. And I said, well, I don't think your prelude pump's going to get up to 99 pounds. Why don't you bring that back down to 10 or 20 pounds? And he says, yeah, I think I will. So what we just did was we troubleshot a schematic, but we never had a problem in the schematic. What we had was we had an operator that thought he was actually changing a high safety shutdown point, which happens on a quite regular basis. But instead of changing the high safety kill, they changed the control set point. And it happens on a quite regular basis. So that's one example. Now, maybe everything right there was programmed right, but his answer was, well, it never preluded. That takes us to a whole different part of the schematic. Somewhere over here on this page. So now we're looking at a different part of the schematic. He says, well, the light didn't come on, but it didn't prelude. Okay, so here's the outputs for our compressor prelude. I say, okay, man, here's an output module. Let's see, look, let's just trace out the schematic real quick. We got a 103 going through an emergency stop switch coming out of a 108, coming through and bringing 24 volts to output module 4 on the power supply. So if the ESD button's not tripped, we should have 24 volts here no matter what position's going on as long as the power's paneled up. So there's going to be our first check that we make with a meter. Do we have 24 volts here at this point? And if he says yes, I'm going to say, okay, well, you got 24 volts there, so put the system into start mode. Try to start it. Does output module 4 light up? He says yes. Okay, do we have power coming out? He says yes. Okay, great. If we got power coming out of output module 4, we should now have power at 110, which is a flyback diode. So I said, find that flyback diode 110 and 102 on the PCB and measure voltage between 110 and 102. So he finds it, puts his meters there, and he says, hey man, I ain't got nothing there. I ain't got no 24 volts. I said, you don't? He says, no. All right, well, but you got power here on the output side on 4 negative on the output module. He says, yeah, I do. I said, did you have wire 109 hooked up there? And he says, oh, yeah, I do. Okay, so there's one missing link. It's called a fuse. So I say, well, hey, do me a favor. Is that output module still lit up? He says, oh, yeah, it's still lit up. It's still in the prelude mode. I said, well, look up at that relay board. Now I'll back up a little bit. Oop. Here's our relay board, right? If I go back forward to page 6, I'll tell you exactly what fuse it is. So this one happens to be fuse 4. It's a 2 amp. So there's fuse 4 right there. And I said, well, hey, go find fuse 4. And I might give him a little pointer and tell him where it's at exactly. And he says, hey, man, there's a red LED on by that fuse. And I said, well, that means the fuse is blown. So each one of these fuses has a nice little red LED beside them. that lights up when that fuse is blown. Now, to explain that to you a little bit, let me jump back forward. Oop. So the first thing that has to drive that red LED on is, one, it needs to be receiving power to this end of the fuse. Second thing for that LED to light up is there has to be a load downstream. So if this was an open circuit not connected to a coil out there on the skid, he would never have seen that red LED. The beautiful thing about it is, at that point, we just troubleshot that part of the circuit and found out that they had a blown fuse. So they replace the fuse. If they blow another one, then we might have a short going out of where that circuit happens to leave the ultronic panel, go through conduit out on the skid to a solenoid out on the compressor package to activate the preloop pump. Any questions? Does anybody have, we got about roughly 45 minutes left on this class today. I can sit here and bring up another scenario or two, but I'd love it if anybody wants to ask about a particular problem that they had. I'd be glad to bring it up and kind of give them something that's not just stuff that I've dealt with, but stuff y'all are dealing with. Or I'll keep moving. Okay, I'll keep moving. So here's another fun little circuit here. On this particular application, the customer has two safety valves. Now, they have a fuel valve for their engine that's controlled by the engine system. They also have a start solenoid valve that's controlled by the engine that controls when the starter engages and when the starter doesn't. But the request was this. They said, we want to add two redundant safety valves on the side of the skid. So what do they use? They use like an automatic Bennis valve is the brand name. There's several valves that do the same thing. We energize them to open. So we're doing the same thing, 24 volts to a solenoid. So the request was this. They want to make sure that they shut off the gas supply to the engine at a fault. The second thing is they say, hey, when the engine's up and starting, once it's finished starting and we know it's running, we want to shut the supply gas off to the starter. Now, the whole reason of this was a rash of fires that started in some of the wetter shale areas where the gas is very, very high BTU, has a lot of good, strong, wet gasoline already coming into the gas, into the scrubbers, extremely volatile, high BTU, very flammable, more so than some of the standard stuff in some of the older shales or the older formations throughout the North American United States. So these guys were being plagued with engine fires left and right on skids in a pretty bad manner. So this is a little circuit that we designed. So we can see that this coil is for the start gas valve. So let's zero in on it first. It says energizes for start gas. That's the only note we have. We know it is grounded. We know that it must receive 24 volts on this 116 to get 24 volts. But let's see what it goes through. If we go backwards, and this is where I say I like to go backwards when I'm troubleshooting a schematic a lot of times, because here's my source. Here's what's supposed to happen. Why isn't it happening? Why aren't I getting 24 volts to my valve? So the first place it goes to terminal 14 of the CR7 relay. It's labeled start gas valve. It has to get power from terminal 11 on the same relay. That gets its power from output module 3. And we read some notations earlier when we were going through that little PowerPoint presentation on this same output module. It says close at auto start, open on fault, 0-second open delay. And then there's an option. So we'll cover this option here in a few moments. So the rest of the power comes from another fuse, fuse 5 on that PCB, and it comes from ESD. So what we might do real quick is, hey, unit's down, unit's not trying to run. Do I have power at 3 positive? If I don't, I need to go backwards. Is my fuse good? Do I have power on both legs of my fuse? Do I have power at 108 coming off of my ESD switch. Power on 103, going to my ESD switch. Believe it or not, those contacts on those ESD switches are really bad about vibrating and failing. Let's assume I have power here. So now I put it into start mode. Does this output turn on? Close that auto start. No delay, didn't mention it, so it should come on immediately. Yeah, it came on. The LED came on. We got power here. Okay, cool. Oops, wrong button. So once we got power here, did we get power here? Well, this one's a little bit hard to measure because we can't get to this terminal per se because it's really inside the PCB. But what we can do is we can come up here where wire 114 on wiring harness 2 enters into the PCB. There's a little white plastic connector there. So if we can identify the wire, understand the pinouts, and I have information like that available, we could put a meter there to see if we're at least getting power up to the PCB. But we could probably assume so. But wait, we also know that we have to energize this relay to close it. So it says page 6. We can jump right down here because we're already on page 6. And here is the start gas valve coil, CR7. It also gets its power from the same source. So we could simply look at the blue LED that's beside this relay and see if it's lighting up. If it's not, but we know we're getting power to it, it could simply be the DE1 wire. So it has to get a ground from digital output 1, programmed to be controlled by channel SO1 low control set point. So what's one really good way to test it without ever looking at our program? While this LED is on, this relay is not energized, we could simply make a jumper wire and we could jumper digital output 1 on the DE3000 terminal board to ground real quick. That's a safe maneuver we can do. Does this relay turn on? If it does, we know that something's wrong with this digital output. The first thing we're going to do is we're going to extract the the first thing we're going to do is we're going to look and see how the low control set point's configured through the menu, because that's the quickest thing we can do. If it looks like it's right, the second thing we're going to do is we're going to extract the program. Too often not, what I find is that somebody has gone into the program and messed with it, and they've actually turned off the checkbox that allows that digital output to turn on. Just so we can mix a little software with today's class. If any of you are having a hard time following me on that, I will pull up that example real quick. We'll just configure a new. We won't dally around. We'll go straight into channel SO1. And so what we're looking for on this case is a low RPM control set point set to turn on digital output 1. So there's the checkbox that I'm telling you that some people forget why it's on, and they might turn it on or uncheck it. We have that happen quite often. People get into these programs and they don't quite understand what's going on. So if that's unchecked, that digital output will never work. So let's talk about the rest of the schematic and talk about how it works. It closes at auto start, open on fault. It opens on fault with a 0-second open delay. So let's just assume those two lines are correct. So as soon as we put it into start, this turns on and we get 24 volts out the other side. We get 24 volts to this relay. We get 24 volts up to this contact and this contact. This is the DE status relay, CR8. Notice it's normally closed. So let's go look at that relay coil real quick. It shouldn't be far. Here it is. Relay CR8, here's the coil. It goes to digital output 8. It says closed when DE faulted. So we know that when we're at a fault mode, we turn on this relay. So if we're in an auto start mode, we're not at fault. So this contact should be closed. So as soon as we get 24 volts here with the red LED turning on the power supply module, we should have power all the way through this contact up to 115, and our fuel gas valve will open. Likewise, if our RPM is less than, let's say, 500 RPM, this should be turned on, where now we have 24 volts and a ground, so this relay should be energized. So we should get power through this CR7 contact because this will change state. Now, we should have power at 116. So 116 should allow the start gas valve to open up. But let's see what happens. So the unit, again, the start sequence is being controlled by the engine. These are safety valves for fire prevention. So the engine starts cranking, it hits, it starts up and starts running, the RPM ramps up to, let's say, 700. Well, that's greater than 5. So as soon as our RPM is greater than 500, this digital output will turn off. This relay will de-energize. These contacts will go open, and now the start gas valve will close. So there's no supply up to the starter system on that engine. So if there's no gas there, the theory that these customers have is that it can't catch fire. Like the theory. No fuel source, no fire. So on a shutdown event, what's going to happen? Right now, if we just follow these two lines, nothing down here. Because, one, we go into a fault, the DE8 relay is going to energize, and this is going to throw this contact open, so now the fuel valve shuts off. Another thing, if this goes open at 0 seconds on a fault, this goes open, so there's not 24 volts anywhere in here, not up to here, not up to here. This contact, when opened, blocked it, so even if there was 24 volts here, it's not getting through to the fuel valve. Anybody disagree with that? So let's say we had a case where the customer says, well, yeah, we want it to work like this, but we're also using this valve to supply gas to our pre-lube, thus our post-lube motor, so we can have a post-lube so we can cool our turbos down when we shut down. There's a great fix for that. This output, digital output, our output module 3 can be programmed to a 60-second off delay option. It says so right there for post-lube. So let's say they do that. So now at fault, this stays on for 60 seconds. This relay, because we're at a fault, still energizes, throws this contact open, so we lose fuel gas here. We cannot have a fuel gas valve on. It closes if there's no voltage. But the RPM goes from a running RPM below 500, which is our set point, and this relay, because it still has power here now, is reintroduced to ground, will turn back on, and now this relay closes again, allows the start gas valve to come back open, allowing a gas supply source for a post-lube pump motor. This is one of the schematics or circuits that was dreamed up sitting in a hotel parking lot at midnight one night. So anyway, so I've got 2:30 on my end. I'm showing we've got 30 minutes. I'm running out of ideas to show you. If anybody has any questions, this is a great time to start question and answers. Allow me to help troubleshoot something else for you. But the bottom line is just some examples of the symbols in schematics, how to read them, how to use them, how to I guess you will, if you understand how they're supposed to work and you can connect the dots and connect the notes, how you can read them. But I'm happy to, at this point, I'm kind of running out of my own original ideas. I'm happy to answer any questions, or if you want me to look at a different schematic, or if you just got kind of a case in point, I'd like to open up the floor for open discussion right now.
Questions for Mr. Nance?
David, I may have just put them all to sleep.
I think you got them. Pique their interest, John. Why don't you go ahead and maybe just run another scenario here that you might have, John, and then we can then reconvene for questions and then wrap if necessary.
Okay, I'll see if I can't dream something up.
Okay.
So we covered the points, kind of individual icons and whatnot like that. But rather than going through that PowerPoint, I'll kind of just do a quick review real quick. Page 1, here is our bill of material area, our option area, our notes area. Always on every page is going to show, and I'll go on and zoom in on that because there's a little bit more information I'd like to show. Well, I must have zoomed in quite a bit. One of the things I do like to point out, besides just the drawing number in this title block, it'll show the date that the drawing was originally done. It'll show you how many pages are there, but it'll also show you the guy who did the drawing. See, there's something else of interest. Page number for sure. It's nice to know what page you're on. And again, the revision section. Again, here's page 2. So we've got a pretty good detail how the enclosure layout is. Front view, side view, accessories, a back pan view. This would be what's inside the panel behind this wonderful door here. Stand dimensions. So if somebody's asking you, well, what are the dimensions of the panel, so we know how to go on and lay out things for the panel to bolt to, that information's here. Sometimes a little bit extra page that's been thrown in to show extra information about the DIN rails and what's mounted to them, and some wiring information even. Again, here's that PCB. We know that by looking at this, that the top plug connector on it is relay wiring harness 1, wiring harness 2. We talked last week about relays. Here are the relays, but they are not in a particular order. They are labeled here, CR2, 3, 1, 4, 6, 8, 7, 5. They are not in order, 1, 2, 3, but here's our power relay, referred to as PR1. Please note that if you run into a panel with this board in there, this is that 10 amp relay cartridge. So remember last week I was showing you the icons on these. All of these other relays have an icon on them that shows it as a double pole, double throw. This has an icon on it that shows it as a single pole, double throw. It is 10 amp, cannot be used in place of any of these other relays and vice versa. Damage can occur to the system and or certainly some problems with the systems if you put one of these relays in any of these other locations. Page 3 in general, I like this page because not only does it show kind of an image of what the terminal board looks like and a slight image of what the power supply board looks like, but it gives great detail of information, not only just what's supposed to wire to that channel the way it was designed, but it also gives us some great information about all the dip switch settings for each individual channel. Unless things have been modified and deviated, as long as that hadn't happened, if you're replacing the component, you can just use this drawing to set your dip switches up for your new terminal board. Over here on this section, I'll zoom in a little bit. It does give us a great representation of what's going on between channel 1 and 30, what that channel is supposed to be, what type of channel that's configured as, in this case 0 to 5 volt or analog, normally open or normally closed type channels, K-type thermocouple channels, etc., etc. It also gives us pressure range, what type pressure transducer has been using, and the original program, how it was configured, whether it was Class A, Class C, or B. It gives us some information about what we're doing with the digital outputs. I'm sorry, not digital, the output modules. It also gives us some wonderful information. This is a very generic panel that can be used with a series of engines, pretty much all Caterpillar engines. It gives us the pulses per revolution, which is just the number of teeth on the flywheel. Again, a telematics module. Our pressure transducer details. I think we covered that one pretty good earlier. The meat and potatoes, the wiring, and again, note, customer 24 volts coming into block 100, block 102. That's almost generic in every Altronic panel. We come from block 100, which is identified by a PCB, through a Chevron, which indicates it's a wiring harness connection, 1 or 2. We tell you it's still wire 100, which is true. It's not changed. Still wire 100, but now it's part of wiring harness number 2. Goes into a switch, wire 101, wiring harness number 2, enters back in through the connector onto the PCB, goes through a fuse, still on the PCB, but now it's wire 103. Anytime you see a group of chevrons, it'll be identified if it's still part of the wiring harness. If it leaves the panel in any way, see if I can't find one, eventually we'll have a colored wire. I don't have too many of those. And that's just to prove that the PCB really did its job, because its purpose was to keep us from having to wire up a panel. Most of these are all part of the PCB or the 2 wiring harnesses that are on the PCB. Several different engine interface pages. I could zoom in on a speed circuit if you'd like. This one's kind of tricky. Oops. Also, too, while I'm back here on this engine interface page, notice what we'll do here. In this case, this is the start signal input to the CAT. We say Altronic controls panel will ground for auto start. CAT must be in auto mode. So there's a switch on this engine that says start or auto. Unground for normal stop. Note, there's notations like this on just about any engine interface page, no matter who the engine is. But remove wire P615 from mode switch, aka rotary switch, insulate and tape back. Why is that? That's the original wire that if the Caterpillar original switch is rotated into the start position, will ground this terminal. We do this for 2 reasons. 1, we don't want this terminal grounding before we send a driven equipment radio signal. Also, we have seen cases where somebody puts a jumper wire back in between 15 and 17 to give it a permanent driven equipment radio signal. We found out that if somebody can figure out how to make something run, that's their most important thing, not necessarily to prevent it from crashing. So the last thing we want is if somebody accidentally came in and put a jumper wire between 17 and 15, or did it intentionally just to get a unit running, but was dependent upon the electronic panel staying in auto for us just to stop and start the unit, that's fine, it works. But then if they don't have this wire removed and somebody comes back and rotates that switch one click to the left or right into the start mode, they just effectively bypass the electronic system, and now the electronic system cannot and will not shut the unit down. So we always add little notations in the drawing trying to go that extra mile to be a little bit extra safe. I'm gloating a little bit, but I talked to a gentleman this morning that had a problem where a unit didn't shut down on one of my competitors' products because they didn't have a notation like that in their drawing. So we'll look at the speed circuit real quick. So in a lot of these cases, we like to control the engine speed both manually and auto. Pardon me for that. I bumped my microphone. But this is a fun little circuit, but a very difficult one to read. It's drawn in more of a point-to-point. If you noticed, I think our units I referred to, and I probably skipped this earlier, I look at the electronic panels as kind of the way we follow our schematics is more of a ladder logic / point-to-point hybrid system. To me, I can follow the ladder logic and they tell the story, but they also tell exactly where each wire goes. So personally for me, it's one of the easier schematics to follow in the industry. And I've been challenged by a few people, but that's just because they learned on another system. But once people take the time to learn this, they start seeing things the same way I do. This is a speed circuit to interface with a 3500, and we have a couple of notes here. Originally, that engine has its own potentiometer to control speed manually, and all they're doing is just sending the variable 0 to 5 volt signal. And so the first thing we've telling them to do is we want you to remove some wires. So we tell them to remove the cat volt 5 volt signal wire from cat terminal 6 and insulate. And we do the same thing, cat potentiometer signal wire from terminal 7 and insulate. So we want them to get those wires off. Then what we're doing is we're using 5 volts from our DE3000 system. Remember, we have 5 volts that supplies all the pressure transducers. Why not utilize it? And we route it through our own potentiometer. It's generally a 50K ohm potentiometer with 10 turns to it. So it's not real touchy. And we return one end of it to ground. Now that potentiometer works just like a pressure transducer for those of you who sat in on that class with me. And it has a variable signal wire. That signal wire will be 0 to 5 volts. And it routes in through our panel onto the PCB. Notice the chevrons, and onto terminal 12 of the auto speed relay. It returns out through a normally closed contact on our common contact, terminal 1, and we say, hey, hook this back up, this signal from the PCB. Now it enters a wiring harness back into cat terminal 7 where we told you to disconnect it from earlier up at the top. So all we're doing is we're using our potentiometer, which is much less expensive than cat should it fail, and we're substituting it in. That's it, plain and simple. Now what we do, we covered this a little bit earlier in this same chapter, where we did a little Ohm's law and we converted 4 to 20 milliamps. What we want to do with this circuit is we want to substitute in and be able to send an auto speed signal. So when we flip that switch that's shown over on page 6 on, we energize this CR1 relay and throw this contact open. Close this contact, and now we've substituted in a auto signal through the same relay. And again, CR1, we're drawing it twice in 2 different states, but there's only one terminal 11. And we substitute in that auto speed signal. Now what we're doing is we're getting our 4 to 20 milliamp signal off of channel A02 on the DE3000 terminal board, but we're bringing it in and landing it on a special block that has a 249 ohm, you might as well just say 250 ohm resistor and we're shorting the negative side and positive side together with that resistor. And then we continue on the same path, and we route through our relay. The ground doesn't need to be switched, so we just hook the ground up permanently. But the CAD system, in this case, is set up to work from 0 to 5 volts. We're sending a 4 to 20, but we convert it. And for those of you who took the first part of this class, do you remember the formula? So it was 4 times, we used, I think, the term that day 200 ohm, but in this case it's a 200. You can round it to 250. So if we write out 4 milliamps, 0.004 times 250, we're going to come up with 1 volt. And then if we give it 20 milliamps, and we write 20 milliamps out the long way, so where it's 0.020 amps times 250, we're going to come up with 5 volts. So we are slightly limited on the low end. We can only go, when auto, from 1 to 5 volts, not 0 to 5 volts. But most of the time, that's still going to get the customer the range that they want in the RPM. That's a little bit of a tricky schematic. It's a little hard to follow. I think the biggest thing that throws people off again is that we show the same relay 2 separate places in 2 different states, an open state and a closed state. And I think having the 2 11s throws a lot of people off, and that's why I like to kind of emphasize on it. More of the same, just different engines. Again, this panel that I use as an example was designed to interface with about 5 different engines.